All right, this is CS50, Harvard University's Introduction to the Intellectual Enterprises of Computer Science and the Art of Programming. My name is David Malan, and this talk is specifically a look at how CS50 has implemented its AI-based duck using OpenAI's APIs. That is to say, companies like OpenAI and Microsoft and others make available APIs, application programming interfaces, via which people like you and me can write our own code and our own programs on top of services and data that they provide. We, CS50, used exactly that to implement a virtual rubber duck. The past several years, in fact, here on campus physically, we've actually given students actual rubber ducks. And the motivation is something that's familiar to those of you who've programmed before, which is to say, among programming circles, it's a common technique when you don't have a friend, a family member, a colleague to ask technical questions of, when you encounter some confusion or some bug or mistake in your code, to at least turn to an inanimate object on your desk, like an actual rubber duck, and talk to it and ask questions of that rubber duck. And the presumption is that simply by verbalizing and clarifying the confusion you're having or the mistake that you've made, that proverbial light bulb will invariably go off and the duck won't even have to respond with a quack or a squeak or anything else. It's entirely about that process of thinking through more logically the problem you're having. So this technique of rubber duck debugging or rubber ducking is something we actually implemented a few years ago, not only physically on campus with tiny little ducks that we give to students and this massive rubber duck that you might recall looming over my shoulder many times in lecture, we also implemented a chatbot version thereof, whereby here's a screenshot of a tool called Visual Studio Code, or VS Code, which is free open source software that we use in CS50 for students' programming environments. And if students up until recently were to ask a question like this, I'm hoping you can help me solve a problem, the duck would reply only with quack or quack quack or quack quack quack, pseudo-randomly quacking once, twice, or thrice in response. We have anecdotal evidence to suggest that this alone was enough to help students troubleshoot and fix problems they're having, not unlike the physical rubber duck. But those same students were actually genuinely surprised when just a few months ago, seemingly overnight, and actually literally overnight, did this same here rubber duck start responding to students in English or some other human language instead. And that's all thanks to these underlying APIs atop which we've built this virtual rubber duck and a lot of CS50's newest infrastructure atop. Thanks to indeed the daughter of one of our teaching fellows far away in New Zealand, does the duck not only seem to live and breathe, but also speak many human languages now as well. This has already been deployed, as some of you might know, at scale to nearly 115,000 students and teachers around the world, to whom these tools are made freely available, along with all of CS50's free open courseware. That's an average of roughly 20,000 prompts or questions per day, for a total, as of today, of some 4.5 million total questions in all. None of this would be possible without the gentleman you're about to meet, CS50's own Rongxin Liu, and also Charlie and Andrew and Patrick and Carter, so many more of CS50's team, and all of our friends in industry at OpenAI, Microsoft, GitHub, and beyond. So without further ado, this is CS50, and this is Rongxin Liu.
Thank you, David. Hi, everyone. Good to see everyone here. Today, we are going to take a deeper dive into how the CS50 duck is made, building on top of OpenAI's API. If you would like to see the actual source code of the demo I've been doing in this workshop, you can feel free to visit this URL. You can see all the source code or the example I demonstrate during the workshop. And there will be a link to the slide to this particular workshop as well. So remember, the address is github.com/cs50/AI-workshop. Cool. All right, so David briefly showed this simplified version of the diagram of the system architect of the duck. And here is actually the complete picture of the system architect of the CS50 duck. So I'll just quickly go through our system architect. So from the point when a student asks a question, whether it is through CS50.ai, the landing page, or through the CS50 duck built in the code space, or when students use this explain highlighted code feature, everything we consider that a user query, and it all goes to our own CS50.ai server running on the cloud. Whenever we receive a student's query, what we actually do is do some sanitization on the prompt, because we wouldn't want to send any sensitive information to OpenAI, so we actually do PII anonymization. On top of that, we also try to do some prompt injection attack detection because we don't want malicious prompt get processed by our LLM system. So of course, we do some prompt engineering along the line. We actually wrap students' code with our own wrapper prompt, and then we also instruct the LLM to follow certain guidelines. For example, importantly, the doc should not be giving any solution at any circumstances and should not giving too helpful code for student. So with all that, we do all that prompt engineering. We do all the PII anonymization. We actually send that it's kind of like a giant prompt to OpenAI, in particular the GPT-4 model. So we will get back a response from OpenAI, and then we will send that response directly back to the user. That's one cycle. Along the way, we also do some retrieval augmented generation, which we will also talk about that in the process. So what RAG does is essentially trying to inject some more useful information into the prompt when answering student questions, because sometimes this LLM model tend to hallucinate. For example, what it means is the LLM model will try to generate like a fake response, like a seemingly looking correct response, but actually make no sense. We try to tackle this issue as well by using a RAG technique. What we do is we actually create like a vector store of all our lecture captions so that when student asks a question, we will be able to quickly search through the entire lecture caption to find the best relevant chunks of the lecture caption. And then we incorporate that into the prompt and then prompt GPT for a more truthful response. And actually the response will be more aligned to our CS50 lectures. That's a lot. Let's actually simplify a bit, and we will focus on what kind of API was used in this process, and I will provide some demo along the line. So these are the API that the CS50 is used most of the time. There's three major OpenAI API used in this system. The first one is the chat API. What chat API does is essentially it provides chat completions services. For example, the LLM model doesn't really understand the conversation. All it's trying to do is do text generation. So we achieve text generation through the chat API. And for the particular RAG pipeline I just mentioned, we need to employ a embeddings creation process. So we need to actually encode all the lecture caption into like a vector representation and then store it in a vector database. So in that process, we need to use the embeddings API to achieve this. And then finally, I will briefly talk about the assistant API. We don't actually use this assistant API. It is still in beta from what OpenAI just said. But the assistant API will basically allow you to build what we actually build our CS50 doc in just a few lines of API calls. So let's first talk about what large language model is. Nowadays, you have all been using large language model more or less, in particular ChatGPT. These large language models excel in generating images, generating text, songs even. In our workshop, we only focus on text generation. So this LLM model will be able to generate a text given a particular user input. For example, if I ask a question, what is Flask? From the perspective of the LLM, it doesn't really understand this is a question. It only sees, oh, here's a lines of text says, what is Flask? And then question mark. Maybe I should complete the text with some text. Human interpret it as an answer, but the LLM model is actually trying to complete what I'm just providing to the LLM model. So that's the text generation aspect of the LLM model. And CS50 is essentially a chatbot, but it's a chatbot with context. It knows about CS50. It knows about what answer makes more sense to the student rather than giving like a totally unrelated answer unrelated to CS50. And when we talk about the LLM system, there's a three role we really need to pay attention. It's called the system, user, and assistant. What system is? System roles basically provide a guideline to the LLM model in affecting its response generation process. So for example, the system prompt, it's a guideline, general guideline to the LLM model when generating a response. So in CS50's duck example, we instruct the LLM model to never give code solution to a student. That's the general guideline. And also not violating any academic honesty guideline. That's also a guideline we provide to the LLM model. We instruct the LLM model. So the LLM model will always pay attention to this particular system guideline when generating its response. User, meaning student, teacher, or anyone interacting with the LLM system, user are the one that actually provide the input to the LLM system. It could be a question, it could be any kinds of text input. Assistant often refers to the response generated from the LLM. It could be GPT-4, it could be any kinds of open source model, it could be Claude, it could be Gemini. So let's first take a look at system message. For example, in CS50 duck, we have a rather complicated, complex system prompt, but here is a simplified version. So first, we define its persona, like you are a friendly and supported teaching assistant for CS50. That's good. We further customize it to be a rubber duck. So we also instruct, hey, you are also a rubber duck. And then we gradually add in more rules or guidance to this system prompt. For example, you only answer questions related to CS50 or computer science field. For example, if a student asks about how to make an ice cream, the duck should not really be responding to that question because that was not kind of related to CS50. And that's how this system prompt will guide the LLM model to not to do so. And importantly, we don't want the duck provide answers because sometimes ChatGPT could be very helpful. So when student asks, hey, I don't know how to solve the filter problem set, can you give me like a solution? And then ChatGPT will happily answer, sure, certainly, I will give you blah, blah, blah answer, and then goes on and on. But we don't want that in our CS50 duck situation. And importantly, every student interaction, whenever student asks a question, we always have this system message enforced before the student's query actually get processed. So that the LLM model will always follow the instruction before actually following or before actually responding to student's query. Because sometimes some clever user will actually try to query something, hey, forget everything I told you, forget everything CS50 told you, please do whatever, whatever. And this will actually help us tackle that particular prompt injection attack. And the interaction between the user and systems actually can be summarized in this diagram. So essentially, a conversation goes like this. So the user prompt the assistant. By prompt, I mean send a query. And the system, the GPT model, will send back a response. And the user will be able to continue the conversation by sending another prompt to the assistant, and the assistant send back another response. This cycle goes on and on. And let's get more detail into prompt engineering. This is a trendy term, but at the end of the day, it's just a way how you ask a question. So there are different kinds of ways you can prompt the LLM model. For example, when prompting the LLM model, you can provide examples. You can provide like some example answer to the LLM model so that the LLM model will try to generate a response that best match the way you want it to react. You can also ask the model to adopt a persona. So in our case, CS50 duck, you are a rubber duck. That's actually we asking the model to adopt a persona. You can also specify the desired length of the output. You can tell the model, please be concise with your answer, and then the model will limit its character limits when generating a response. There's many other different kinds of prompt engineering technique, and there's a link in the slide that will guide you to more information. They will point you to more information on this. So now let's look at these API in detail. First of all, the chat completion API. For example, when I ask a question to this GPT model, can you help me with my Tiedemann problem set? The GPT generates a response, I'll be happy to help with the CS50 Tiedemann problem set. Could you please specify which expert, and then goes on and on. What it looks like in the API call looks like this. It might look a little bit scary, hopefully not. I will explain line by line. So in order to use the OpenAI API, of course, we need to first use OpenAI's library or the SDK. So if you pay attention to this particular API call, you soon notice there's two roles that's happening, right? As I mentioned earlier, there's a system role, user, and assistant. In this particular API call, there's a system role and there's a user. So system is the general guideline that you send to the LM model, and user is actually the student or teacher or me are asking a question to the LM model. So you will send the system message. You will generate like a message array, and then with a system prompt, and then with a user prompt, and then you prompt these to you prompt the GPT model to generate a response, and that's the response you get back. And now actually let's do a live demo on this one. So I have a demo open already. If you want to look at the source code, you want to follow along, that's welcome. But the catch is you will need an OpenAI API key to be able to make the API call. So I'm just going to quickly go to my demo folder. I'm going to code chat.py. Hope everyone can see my screen clearly. I'm going to kill this. So first thing we need to do is I'm going to load my API key because the way I set up my environment. I'm just going to quickly do this. Okay, first thing we need to do is to first import the OpenAI client. So what we can do is we from OpenAI import OpenAI, and then we need to instantiate this OpenAI client. I'm going to specify the API key. And now let me actually do one thing real quick. I'm going to disable my GitHub Copilot because it's too helpful. See, this is a disadvantage of using AI tool. So I'm going to reload my window real quick. All right. So what I just did is I import the OpenAI client into the Python script. I also set the API key. Normally, the OpenAI API key would be like an environment variable set in your terminal. In my scenario, I already configure it in a .env file, so I would just load the API key from that .environment file. But importantly, what we wanted to do is to create a check completion project, an object. Check completion equal client. So I'm going to call the chat method completion endpoint and then create a completion. So here, message. Remember, we want to tell GPT what the system message is, what the actual user message is. So here is how you actually can send those information to the GPT model. Here, I'm just going to quickly demo without actually specifying a system prompt. You will need to tell this is a user prompt. So give it a role, user, and then content. I'm just going to say, hello, world. And that's it. I also want to ask OpenAI to actually use GPT-4 to generate a response for me. So I'm going to specify model equals GPT-4. There are different kinds of model you can use. So if you want to refer to the actual API documentation, OpenAI will tell you what kind of a model is available to you. I'm just going to use the latest GPT-4 model that are provided by OpenAI. So now that we have this check completion project created, we will actually want to store the response object in a variable called response text. So again, this is my check completion object. I'm going to access the actual text because the completion object is rather complicated, soon you will see. The reason why I access the zero index of choices is because you can actually have the GPT model generate multiple response, and here we only care about the very first response. Response, text. Okay, let's try to run it, and it might work or might not. So I'm going to run this Python script real quick. This is normally the case. Messages. Okay, message. Try to run again. And see, we get back a response. So because we send hello world to the model, and then the model say hello back. So quickly, we can actually start asking a question here, right? So we can ask, what is Flask? Explain it to me in 3 words. Remember, during the prompt engineering section, I mentioned that you can actually limit the response, you can actually limit the length of the response generated by the LM model, and that's how you can do it in your user query here. So I'm going to update the user prompt here, and I'm going to run this script quickly again. I run it. It gets back 3 words, web application framework. That's very helpful. So naturally, you will like, okay, now that's great. Now I'm actually interacting with this LM model, but then how I can make it more interactive? So naturally, you will start actually trying to dynamically grabbing the user input from terminal or from a web application or something like that. And for the sake of demo purposes, I'm just going to grab the user input from the terminal. So the most straightforward way to do it is actually in Python is to use the input function. So I'm going to store user prompt from input user. And I'm going to put this user prompt here in the content field. I'm going to run it again. It asks me to ask a question. Now, this time I want to ask, how can I make an ice cream? Of course, it go ahead and trying to help me make an ice cream because I haven't instructed to not to do so. But for demo purposes, this is how you prompt the LM model for instructions to get back like an instruction on how to make an ice cream. And because I gathered OpenAI is thinking so hard to generate a response because making an ice cream is not that straightforward. And as you can see, it sent back a bunch of tests telling me how to make an ice cream. Cool. Okay, this is kind of like a one-way interaction. Then you might start asking, okay, how can you build a conversation? And this is our next presentation on how to make a conversation, how to use the OpenAI chat completion API to actually build a conversation chatbot. So it's actually similar to building a one-way interaction chatbot. As you can see, again, I have to emphasize, the LM model don't understand what you say to it. It only tries to complete what you send it, what you send to the LM model. So previously we sent, can you help me with my filter? Let's just say, for example, here, can you help me with my filter preset? This is a input to the LM model. The LM model sees this particular text. It will try to generate a text that best match what you provided to the LM model. For example, here is a response back to generate to the user. In order for the conversation to carry on, we actually need to tell the LM model what you just replied to me, because the LM model doesn't have memory. So what we need to do is literally put its response back to the message array and mark it as assistant role, because it has to tell OpenAI to distinguish what kind of a prompt it is. So we put it back to the message array. And then in order for me to ask a follow-up question, we will actually need to prompt these three lines of prompts, three prompts to the LM model. Actually, it's the four prompts we need to send back to the LM model. So let's go back a little bit. So the assistant response get appended back to the message array so that I can ask a follow-up question. And this will be the new cycle of the conversation. We prompt these four message to the LM model and generate the next response. We also need to store that so that we can ask another question. And this thing goes on and on and on and on. And as you can see, as the conversation progresses, the message array we are sending to OpenAI is actually getting larger and larger and larger and larger. And that's how it can generate a response that seemingly match or seemingly follow the conversation. Because otherwise, the model will have no memory of what you just asked about. And let's go back to the code and see how we can actually code this. So I'm going to check my notes. So because we want to build a chatbot that's interactive, the model will just keep prompting you after it generates a response. So naturally, we want to do a while loop situation here. So one thing we want to do is we want to keep the conversation goes on forever. So we use a while true loop. And the first thing we want to do is we want to grab the user prompt here. And then we also want to create an empty array object to try to keep track of the conversation. So we instantiate a message array on top before the while loop. So first, we want to append what I just asked, what I just provided to the terminal. So we will say row, user, content, and user prompt. Now that the message array has my question or has my user query stored, then we can start prompting GPT to ask a question to get a response. So again, here we no longer need to hard code the user prompt here. We will just replace the message, the actual content with the message array, so that this message array is actually referring to this particular element. It will just keep growing larger and larger and larger as the conversation progresses. These two lines will still remain the same while true. Yep. And so that we can tell what response is from the model, I will just use an F string to help me distinguish if this is a response coming from the model. Assistant, okay, user, that looks good to me. Okay, now I'm going to run this again. Right, so I ask what is Flask in 3 words. Okay, it sent back a response. If we want to test if the model has memory now, we can ask, did I just ask web application framework? Now the model actually remember what I asked, but it's actually not remembering. It's because the message array contains all the conversation history, and we actually keep reusing that history by appending new assistant response and new user prompt to that history, and then we keep prompting the LM model to generate a response. And that's actually how a LM chatbot is built. Okay. So one thing with the LM model is hallucinations. So hallucination generally refer to the LM model try to generate a response that's actually incorrect, but it try to persuade you that's actually the correct answer. You actually don't know the answer at all. And one way to tackle this particular issue is called grounding. We want to ground the model. So by grounding it, we mean we want the model to be able to reference some kind of a source of truth when generating its response. one particular technique that related to grounding is called the retrieval augmented generation, also called RAG. You can think of it as providing a cheat sheet to this particular LM model when generate a response. This is nothing related to fine-tuning. It's like when LM model trying to generate a response, you actually hand the LM model, hey, by the way, here is some information that you can refer to or might be helpful to you when answering the question. Let's just give you an example in CS50's context. So when student asks a question, what is Flask? So Flask could mean anything. It could mean like a musical instrument, but in the computer science domain, it's actually referred to a lightweight Python server framework. But sometimes for CS50 students, like mostly are beginners taking the course, we don't want the response to be so complicated because Flask can have a technical explanation to it. We want to give like a response more aligned to the CS50 course and more beginner friendly. So what we do, we perform a RAG, we perform a retrieval augmented generation. What it means is we quickly search through our entire knowledge base, usually comprised of the lecture captions. We will quickly search through what's the definition mentioned in the CS50 lecture itself. It could be something David said in the lecture. We want that as a source of truth when answering student question. So we quickly do that. We grab the cheat sheet, and then we put it in the prompt, and then we prompt OpenAI to generate a response. So what is Flask is actually not the prompt we send to OpenAI. It is what the updated prompt we are actually sending to OpenAI. So we, of course, the students originally request or the students' original queries in the prompt, but we also inject the useful information we think into the prompt and then prompt GPT to generate a response. And concretely, what's happening here? So first, when this question comes in, we generate a vector representation of this particular English plain text. It's an array of like a numeric floating number with a dimension of like 1536. Now we quickly search against our database to find which particular lecture caption actually best matched to this question. So we found that this particular lecture 9, this particular segment, David actually talking about Flask, the framework. So this is actually one of the caption snippet we have here. So our knowledge base actually contains of tens of thousands lecture caption chunks. It's usually a 30-second chunk. So it's like a 30 seconds of what David said in the lecture. We chunk our lecture caption into those 30-second chunk, and then we also create embedding, like a vector representation of each 30-second chunk, and then we store that in a database. We literally just concatenate everything that's within the 30 seconds interval. We turn them into a vector representation again. Again, this is encoded using OpenAI's text embedding model. The generated vector dimension is exactly the same as the one that gets generated by using students' query. So the vector representation, the vector representation we are getting is always in the same dimension. So when student asks a question, right, we generate vector representation. We use this vector representation to do an embedding-based search against our vector database, and then we retrieve the best matched document. We call it the retrieve document, which is the best matched lecture caption chunks. We inject that back to the prompt, and then we prompt GPT to provide a response. And that's how we actually ground the LM model. And in our production, in our CS50 Duck production, we're actually injecting like 3 best match chunks so that we can provide more useful information or more truthful information to LM, to GPT model when generating a response. And nowadays, people are talking about vector database. We also use a vector database to facilitate storing and searching the embeddings or searching the documents within the database. So one database we chose to use is one of these open source database called Chroma. And this is actually a diagram summarizing the entire query workflow. So again, the query comes in, we call OpenAI's embedding API endpoint, generate a vector representation, and then we quickly search against the vector database in Chroma. We retrieve the best match 3 lecture caption. We put it back to the prompt, and then we prompt OpenAI to get an answer. And next, I'm just going to quickly demo what the embeddings-based search is. And just so we are aware of the time, I'm just going to quickly open the example for you to look at. So here, I'm just going to quickly show you what a embedding looks like for this particular word, cat. And most importantly, this is the API we're actually calling, called the embeddings API. So we, again, similarly, we invoke the OpenAI client, and then we call the embedding service to create an embedding for us for this particular word, cat. I'm going to run this. As you can see, this thing comes back with like a giant vector that makes no sense to me. I don't understand what it means. But this is what it means, cat, from the OpenAI's text embedding model's perspective. And you can say, and then you can see that the shape is 1536. So that's the dimension that this vector representation is. We can actually encode another example. What is Flask? So this obviously is longer than the 3-word cat. But let's see what it looks like when generating an embedding. It still gets back the same dimension of vector representation. So regardless how long your input text is, the generated vector representation dimension is always remain unchanged. And that's actually it's model dependent. So it depends on what text embedding model you use. So you might get back different kinds of vector representation. So if you use a particular model to create this embedding, you must use the same model to also encode your other, cheat sheet or other chunks of document, so that you can perform like a cosine similarity calculation in between these vectors, so that you can get back a score, and then you can use this score to determine what's considered the best matched chunks, so that you can retrieve them accordingly and put them into the prompt. So now that we know how to create an embedding, I'm just gonna go through how you would want to create a vector store, or how you can create a bunch of embeddings for your document and then store them in a vector database. So in this script, if you are following along or with the source code provided to you, what I am trying to do here is actually, I'm trying to read the transcript from a particular lecture. In our example, we are trying to read the transcript from the AI lecture that I taught last year fall. I'm just gonna do a very quick and simple chunking strategy here. So when it comes to RAG, it's also very important on how you pick a chunking strategy. So here, I'm just gonna bluntly like chunk each text every 500 character. I'm just gonna put this giant transcript into like hundreds of like a caption chunk, and each chunk will be like 500 characters long. And this is exactly what the script is trying to do. I'm gonna store this chunked caption into a file called the embeddings.json.l file. What JSON line file means is each line is a valid JSON document. I'm just gonna store all this chunk into one giant file so that I can demo in the next script. So I'm just gonna run this create embedding script. What it's trying to do is it reads in the lecture captions, it chunks them into 500 character long chunks, small chunk, and then for each small chunks, we call OpenAI's embedding API and create a vector representation of that 500 character long chunk. And then we store them into a JSON line document. Or you can store, in this particular stage, you can actually store them in a vector database. And for the sake of demo, I'm just going to store it into a file. And now that it finished creating the embedding, I can actually quickly show you what it looks like. So if you look at this embeddings.jsonl file, as you can see, the first 500 characters long of the caption has been chunked. And then the corresponding embedding is also being created. So we did that for every 500 characters. And it will come back with tens of thousands, chunks and its corresponding embeddings. I'm not going to finish scoring the whole document because it's kind of large. But you get the idea. Right now, we are building a knowledge database. In particular, we are building a knowledge database containing lots of lecture caption chunks for the AI lecture that taught in the fall 2023. Okay, I'm just going to close this. Now that you know how to create an embedding, you also have a vector representation of all your lecture caption. You want to do a search against it. You want to do an embedding space search. So if I open this example here, what it does is actually trying to retrieve the embeddings document we just created, load them into memory, so that we can perform a quick, simple embedding-based search. And the algorithm we are using here is called the cosine similarity. It's essentially a dot product between the student query and the vector database. So in this for loop, it's actually trying to do a very straightforward search. It literally calculates a cosine similarity between the student query and each of the lecture caption chunks in the embedding file. You can also store that in a vector database. When you perform like a vector database embedding-based search, they have a more fancier algorithm to facilitate a more efficient search. But in this demo, we are just going to calculate this cosine similarity one by one. And that's exactly what this script is trying to do. So if I run this, enter a query, let's just say this is an AI lecture, but I also know that this is a family lecture, so maybe I would type family lecture. And it will try to find the particular caption that related to family lecture. It's not a simple keyword matching. It's trying to do a semantic search. So it gets back this particular chunk, and let's see. So I remember this particular portion of the lecture is actually David interacting with the participant, which is mostly parents, and in trying to find out which particular essay is generated by the AI, and that's how the embedding-based search give us the result. If you perform a keyword search, you actually can't see any words mentioning family in this particular response. So naturally, now that we know how to retrieve a useful document, how can we incorporate back to the chatbot example? And that's actually the next example I'm going to show you. The general process is still remain unchanged, right? When you're chatting with the chatbot, it's just underneath the hook. When I send a question to the AI model, before we actually pass it along to the GPT-4 model, we intercept it. We quickly do embedding search, get back some information, put it in the prompt, and then prompt GPT. And that's actually what this example is actually doing here. Still the same thing, load up the embeddings, do an embedding-based search. But importantly, we update the prompt here. So importantly, we are actually building the prompt. So when student's query comes in, we do some processing on top of student's query by injecting extra information on top of it. I'm just going to run it again. So what is minimax? Let's see how it goes. So when I ask what is minimax, this particular lecture caption actually get retrieved. It actually get injected to the prompt. And that's actually the entire prompt we are sending to OpenAI. not just a simple question, what is minimax, but the entire prompt that we just updated. So OpenAI now generated a response back to me, but OpenAI is actually generating a response using my updated prompt with the provided information in the prompt. Now that's a lot. Like you need to come up with a way to create embeddings, and then you need to find like a vector store, you need to pick a vector database to store those embeddings. So OpenAI actually has this recent API called the Assistant API. It basically simplifies this entire process. So you build an assistant, you can also create a vector store quickly and then attach to this assistant. So when this assistant trying to interact with the user, you will be able to utilize the vector store you created and then quickly retrieve relevant document and answer the question for the user. And you don't actually need to worry about implementing the chunking strategy. You don't need to worry about when you should utilize this vector store. The Assistant API will automatically do that for you. And I think it's worth demonstrating here in this workshop as well. CS50 is actually not using any of the Assistant API, but in the future we might. So here, I'm going to remove OK. So here, what I'm doing here in this script, so first, I want to create a vector store, which is the embeddings that I wanted to provide to this assistant. So what I'm doing is I literally upload all the lecture transcript one by one to OpenAI, because we need to first upload the file to OpenAI so that the OpenAI vector store can use it for the assistant. So this three lines is essentially doing go to the transcript folder, grab each transcript, upload it to OpenAI. Once we have the file uploaded to OpenAI, we can now build the vector store. So you can associate this particular vector store with any kinds of file you want, as long as they're uploaded to your OpenAI account. In this scenario, I want to associate all the lecture caption I just uploaded, and I'm going to create a vector store. This vector store, you can think of it as a vector database, like a tiny vector database sitting on OpenAI's server that will allow you to be used by the assistant you're soon building. Now here, we want to build an assistant. And importantly, we want to give this assistant instruction. Again, this is the system prompt you're actually writing right now. Here, I'm just going to give it the same example I showed you in the slides. Those are the simple guidance I will be providing to this assistant. I call this assistant CS50 duck. I also tell the assistant, here are the tools you can use. You can do a file search. The OpenAI document also tells you what kind of a tooling it's supporting currently, and you can refer to the document if you want more detailed information. Here, we only care about searching file. In particular, we care about searching lecture captions. So now that you specify, OK, you can do a file search, OK, fine. Where should I search? So here, you will say, OK, please go search this particular vector store. So the vector store we just built here, containing all the lecture caption. I'm going to attach it to this assistant. So that now you can think of, OK, I'm a CS50 duck. I'm a friendly supported teaching assistant for CS50. I'm a rubber duck. I should not do blah, blah, blah. And when it comes to searching file, OK, I'm going to look at this particular file store to grab information that might be useful when answering questions. That's basically what these lines are doing. For the next two part, it's a detailed implementation for this particular API. So thread, it's recorded in previous example, I built a message array to keep track of the message. In this new API, Assistant API, there's a thread API you can use to maintain the conversation history. So it's basically OpenAI help you keep track of the history so that you don't need to worry tracking them yourself. Of course, in production, you will also want to keep track of the history yourself when building LLM system. And each assistant interaction is considered a run, so that's why we also need to invoke the run API. Don't worry too much about it. What it means here, the important takeaway here is the picture of how you can build an LLM system with RAG. So this particular while loop doesn't actually relate to our demo here. It might be beyond the scope. So what it's trying to do is once you invoke the assistant run, we will need to periodically poll the run result. And when it's completed, we can send back the response back to the terminal or back to the GUI, however you implement. But for demo, I'm going to run the demo directly. I'm going to run a different version. So what it's doing right now is, okay, now I'm uploading all the lecture caption to OpenAI. OpenAI take care of creating embedding for the thing I just uploaded. And it creates a vector store, and then it also creates an assistant with this particular vector store attached. Now it is ready for me to interact with this assistant. So I can just ask, when did read row get mentioned in lectures? If you ask this question in ChatGPT, it might not know because it was just trying to hallucinate. But because we provided this assistant with the full transcript of the 2023 fall lectures, and David did mention Rick Rowe somehow, apparently here in one of the lecture, at the end, I believe David, put out like a QR code something, and then student can scan it, and it's actually a Rick Rowe song. And actually, the assistant was able to utilize the transcript to provide an answer, and it's actually a truthful answer, and it was able to cite you, okay, this is actually the source I'm referring to. In this particular chunk of the caption, Rick Rowe did get mentioned. And last but not the least, with all this low-level API implementation, I just wanted to show you one feature that OpenAI nowadays also available. In a GUI approach, you can also build the same thing I just did, but not writing code at all. So this is actually an interface of the GPT's Builder interface. So in the ChatGPT website, you can actually build your own assistant right through their web page. You can literally tell you what you want to do, what you want to build, and what kind of a personality you want to give it, like what kind of information you want this particular GPT to use. In this example, I said I want to create a CS50 duck, and GPT Builder suggests, okay, let's call it CS50 duck. Cool. It then go on and start generating like a avatar for me, which looks kind of cute. So if I keep goes on and on, I can actually finish building the CS50 duck within the GPT Builder. And this GPT will be able to deploy and get used by the OpenAI user globally. And I think with that, I hope you get a better sense of what's actually happening underneath the hood when interacting with this LLM model or interacting with CS50 duck. These are the building block. These API are the building block of CS50 duck. And for sure, you can also repurpose it to build another LLM system that better suits your needs. And with that, thank you for attending this AI workshop. And this is CS50.